Hi everyone, this is Dr. C. Manjunath. I'm an associate professor in the Department of Chemistry, RV College of Engineering, Bangalore. So, in continuation to my recording about computational chemistry, so far I have covered the introduction, about computational chemistry as a first part. In that, I have discussed about the molecular modeling, scope, cost, and efficiency. And I have discussed in detail about the molecular interactions, both covalent and non-covalent. And in the second part of the video, I have covered molecular topology, where I have discussed about various matrix representations like vertex adjacency matrix, edge adjacency matrix, distance matrix, weighted adjacency, weighted vertex adjacency matrix, etc. So I'll be continuing with the topological indices in this third part of this unit, the recording. Let me go to that slide. 59. Yeah. Okay. Topological index. So we know that the graph is the chemical molecular formula or structural formula is represented in the form of graph. It is having atoms and bonds, and those structures are represented in a mathematical form by matrix representation. So one is vertex adjacency matrix, distance matrix, and edge adjacency matrix. And these are discussed so far in the previous video. And here in this video, I'll be discussing numerical descriptor and topological indices. So this is the third part of the recording. And in the fourth part, I'll be discussing about this property prediction, that is QSAR or QSPR. Structure activity relationship, the quantitative structure activity relationship, and the quantitative structure property relationship will be discussed in the next recording. So in this, I'll be discussing about topological indices. Okay, so why topological indices? So we know that the matrix that we have discussed in the previous recording, it is having large number of large amounts of data, and difficult to compare molecules directly using the full matrices. So we need a single numerical value to represent the molecule or a graph of that molecule. So these individual simple numerical values are called topological indices. So it's a topological index is a numerical value derived from a molecular graph and from their matrix representations. It depends only on the connectivity, not on its the orientation in 3D. It's not on geometry. So these topological indexes are basically calculated by using adjacency matrix, distance matrix, and a vertex matrix that we have discussed in the second part of this recording, this video. Let us look at how the matrices, these matrices, lead to topological indices, means some numerical value. So from adjacency matrix, we obtain vertex degrees. Vertex adjacency matrix, from that we get vertex degrees. These vertex degrees are used to calculate Zagreb indices and also the plot number. So these are the two topological index that we have discussed, that we are discussing in this. And from the distance matrix, so it is to obtain inter-vertex distances. This matrix is used to calculate the another topological index called Wiener index. Let us first understand the Zagreb indices. Zagreb indices are degree-based topological indices. It's used to quantify the molecular branching and the connectivity from a molecular graph. So actually there are two types of Zagreb indices. The first Zagreb index is represented by M1. It is defined as it is the sum of squares of the degrees of all vertices. Okay, you find out the degree vertex, identify the vertex and identify its degree, square it, square of the degrees of all vertices, and then add all of them. So you will get one number that is called Zagreb index for a molecular formula. So the formula is very simple. M1, first Zagreb number. I is a vertex from 1 to n. And degree, it's a sum of the squares. This is the sum and squares of the degree of vertex I. So n is the number of vertices, degree Vi is the degree of vertex I. Then the second Zagreb index M2, it is defined as the sum of the product of degrees of adjacent pairs. So products of degrees of adjacent pair. First, identify the vertex, identify the degrees, and identify the adjacent degrees, and calculate the products of degrees of the pairs, adjacent pairs. Excuse me. Then add all of them. So you'll get Zagreb index M2. So M2 is equal to I comma J. These are the two adjacent vertices. Its degree, the degree of the vertex I into the next its adjacent vertex, degree of vertex J. The product of these two, the degree of vertex I into degree of vertex J, the product of these, and then you should add continuously to the next neighboring adjacent vertexes. So is the set of edges called bands. Okay, let us understand Zagreb indices by taking pentane as an example. So pentane, the formula is C5H12, and its molecular graph is represented like C1 to C2, C3, C4, C5. It is having 5 atoms, 5 carbon atoms. Okay, so then identify the vertex. So there are 5 vertexes: C1, C2, C3, C4, C5, and the degree. Degree is the number of neighboring atoms to which it is attached. For example, if you take C1, right? C1, it is attached to only C2. So therefore, its degree is 1. But if you consider C2, it is attached to C1, C1 and C3. So therefore, its degree is 2. Then if you consider C3, the third vertex of the pentane, it is attached, C3 is attached to C2 and also the C4 carbon. So therefore, its degree is 2. So similarly, C4 is also 2 and C5 is 1 because C5 is C4 is attached to C3 and C5, and C5 is attached to C4. So this is the degree. So degree of vertex, the number of atoms to which it is at. Once you identify the degrees, right, the Zagreb number 1, M1, what is that? Sum of the squares of the degrees of the vertexes. So this is the degree of the vertex 1, C1, C2, C3, C4, and C5. These are the 5 vertices. So the degree of C1 is 1. So therefore, the square of that is 1 square. The degree of C2 is 2. So 2 square. It's 2 square for C3 and 2 square for C4 and 1 square for C5. So 1 square plus 2 square plus 2 square plus 2 square plus 1 square. So is equal to 1 plus 4 plus 4 plus 4 plus 1. It will be 14. So this is the Zagreb number 1, M1, for the pentane. So let us calculate Zagreb number 2, that is M2. Okay. For this, you have to identify the edge because you have to identify the degree of the neighboring vertexes. So in this, we have C1, C2 is one edge, then C2, C3 is another edge, C3, C4 is another edge, and C4, C5 is another edge. So there are total 1, 2, 3, 4, 4 edges, right? 4 edges. Then once you identify the edge, okay, then the edge sharing vertices C1 and C2, identify the respective degrees. So this is for the C1 is attached to C2, therefore its degree is 1. But C2 is attached to C3 and C4, its degree is 2. So this is the C2 degree and this is C1 degree. Then 2, C2 has 2 degree and C3 is attached to 2. So therefore 2 into 2, the degree of each vertex attached to edge. Then C3 has actually 2 degrees. It is attached to atoms, and C4 also attached to 2 atoms. Therefore, its degree is 2. then C4 is 2, and C5 is attached to only C4, its degree is 1. So then we should take the product of this. 1 into 2, 2, 2 into 2, 4, 2 into 2, 4, 2 into 4, 1. So the sum of all this, 4 plus 2, 6, 6 plus 4, 10, 10 plus 2, 12. 2 plus 4 plus 4 plus. So this is the Zagreb number 2. So this is how we calculate the Zagreb indexes for the given molecule. So the interpretation from this number is if M1 increases, Zagreb number 1 increases with vertex degree and branching. So if the branching and vertex number of degree increases, obviously the M1 increases. M2 reflects the bond connectivity between the high degree of atoms, Then the branched isomers have higher Zagreb indices than linear ones. Let us calculate the Zagreb indices for the isomers. Like, let us take this as an example: N-pentane, isopentane, or neopentane. These are the isomers of isomers. They have the same molecular formula, but they have a different structure. So this is the graph. You can say that the pentane, and this is isopentane and neopentane. So N-pentane is a linear chain. The isopentane is moderately branched. This is the only branch. And neopentane is highly branched. It's tree-like. So 1, 2, 3, 4. Okay. So let us calculate M1 and M2 for this these isomers. Okay. For that, first you should identify the degrees for the N-pentane. N-pentane, for example, if you take this as C1, C2, C3, C4, and C5, and if you label this as C1, C2, C3, and C4, and C5, and this one as C1, C2, C3, C4, and C5, right? If you number it like this, then let us find out the degrees. So these are the vertices, okay, of all these molecules. C1 vertex is 1 because it is bonded to only C2. C1 degree. This 1 is a degree. So this is the degree of vertex. Okay. C2 is bonded to C1 and C3, therefore its degree is 2. And C3 is again bonded to C2 and C4, therefore its degree is 2. C4 is bonded to C3 and C5, 2. Okay. C4 degree is 1. C3 is degrees 1, 2, 3, 3. And C5 degree is 1. C5 degree is 1. And C2 degree is 2. C1 is 1 in this case, in case of isopentane. In case of neopentane, C1, okay, C1 degree is 1. It's attached to only one atom, okay, one atom. C2 degree is 1. C3 degree is 1. C4 degree is 1. But this C5 degree is 4. C5 degree is 4. Okay, so 1, 1, 1, 1, 4. 1, 1, 3, 2, 1. Okay, and 1, 2, 2, 2, 2. These are the degrees. Once you identify the degrees of each vertices, okay, you can calculate. So M1 is the sum of the squares for the N-pentane. 1 square plus 2 square plus 2 square plus 2 square plus 1, it will be 14. So then 1 square plus 3 square, 9. 9 plus 4, 13 plus 14, 15, 16. So this is the Zagreb index. Then 1 square plus 1 square plus 1 square plus 1 square plus 4 square. 16 plus 4, this is 20. So this is how we calculate Zagreb index. Some of the squares of the degrees of the vertices. Then this is the Zagreb number 2 is the product. So degree of y into degree of j. Okay. Then the sum of all those products. Okay. So 1 into 2, 2, 2 into 2, 4, plus 2 into 2, 4, plus 4. Okay, that. So you'll get Zagreb index 12. For example, let me calculate for this one, this M2 for pentane. M2 for pentane. Let me take this board. Okay. Let me. This is C1, C2, C3, C4 and C5, right? So this is 1, 2, 2, the degree is 2, 2. Sorry, let me take this. C1, C2, C3, C4, C5. The degree is 1, 2, 2, 2, 1. So M1 for this is 1 square plus 2. 2 square plus 2 square plus 2 square plus 1. 1 plus 4 plus 4 plus 4 plus 1. This will be 14. Okay. Similarly, M2 for this is let me write here. M2 for this is this is C1 into C2, 1 into 2 plus 2 into 2 plus the degree of adjacent vertices, the product of degree of adjacent vertices. 2 into, this is actually C2 into C3, corresponding to C2 and C3, and C3 into C4, then C5 C4 into C5. C3 degree is how much? C3 degree is 2, and C4 degree is also 2, and C4 plus, this is all plus plus plus. C4 degree is 2 into 1. So 1 into 2, 2, 2 plus 2 into 2 to the 4 plus 2 to the 4 plus 2 ones are 2. So it will be 6 plus 6. This will be 12. Okay. So this is equal to 12. So this is the M2 for pentane. Okay. So let me go for so this is how we get M2. So M2 we get. Let us calculate. Actually, this should be 14. Let me calculate. So this is the wrong. This is actually 14. So let me calculate for isopentane. M2 for isopentane. So M2 for isopentane. Okay, this is actually C1, C2, C3, C4, and C5. So these are the vertices. First, you find out the degree of that. C1 degree is 1. C2. So this is bonded to 1, 2. Okay. C3 degree is 1, 2, 3, 3. And C4 degree is 1. C5 degree is 1. Okay. So M1 for this is C1, C1, C2, C3, C4, and C5. So 1 square plus C2 degree is 2 square plus C3 degree is there are degree is 3 square plus C4 degree is 1 square. Okay, plus C5 degree is 1 square, right? This is M1. So it will be 1 plus 2 2s are 4 plus 3 3s are 9. 3 square is 9 plus 1 plus 1. So it will be, this will be 16, right? So this is 16 for M1. Let me calculate M2 for this. So M2 is the what product of C1 into C2, C2 into C3, C3 into C4, C1 into C2, C2 into C3, C2 into C3, C3 into C5 actually. Then C3 into C4. C1 is C1 and C2 are adjacent. Then C2 and C3 are adjacent edge vertices. C3 and C5 are adjacent edge vertices. C3 and C4 are. So C3 is adjacent to C2, C3, and C3 is adjacent to C2, C5, and C4. So therefore, the C1 degree is how much? C1 degree is 1, and C2 degree is 2. Plus C2 degree is 2, C3 degree is 3. Plus C3 degree is 1, C5 degree is 1. Plus C3 degree is 3 into C4 degree is 1. So this is M2. So M2 is equal to 2 plus 6 plus 3 plus 3. So this will be 14, right? So 6 plus 6, 12 plus 2, so 14. So therefore, the M2 for what is that? This is not 13, this is 14. So let me calculate M1 and M2 for neopentane. So M1 and M2 for neopentane. Okay. So this is 16 and this is 14. So this is the neopentane. Label this as vertex C1, C2, C3, and C4 and C5, right? So this is how I should label. So let me calculate Zagreb number 1, M1. First, for that, you should find out the vertex. So what is the vertex of this? So C1 is attached to directly adjacent to C5. So 1, C2 is adjacent to C5, C3 is adjacent to C3, and C4 also 1. So this is the degree of each vertex because they're attached to one another. But C5, the degree is 4. C5 because it attached to C4, C1, C2, and C3. So C1, C2, C3, C4. Just write this. Then you calculate the Zagreb number 1. So what is that? C1 degree is 1 square. Plus C2 degree is how much? Again 1 square. Plus C3 degrees how much? 1 square. Plus C4 degrees how much? 1 square. Plus C5 degrees 4 square. So it will be 1 plus 1 plus 1 plus 1 plus 16. So it will be 16 plus 17, 18, 19, 20. So this is the Zagreb number 1, M1 for this neopentane. Okay. Let me calculate M2 for this Zagreb index M2. So this is adjacent edge sharing the adjacent vertices C1 into C5. These are the adjacent. Then C2, C5. They are adjacent. C3, C5. They are adjacent. Then C4, C5. They are adjacent. Okay. So M2 is actually the degree of the vertex C1. The degree is 1 into C5 degree is 4. And plus C2 degree is 1, C5 degree is 4. Plus C3 degree is 1 into C5 degree is 4. C4 degree is 1 and C5 degree is 4. Okay. This is actually the formula. But C1, this has to be written only for reference. This C1, C2, C3. So this has to be written only for reference. But the formula is this one directly. You should write here. So this is 4 plus 4 plus 4 plus 4. So this would be 16. So this is the Zagreb number M2 for this neopentane. So this is how we should calculate the Zagreb number 1 and 2 for the various compounds. So this is 16. So this is wrongly printed as 13, but this is 14. So the trend is both M1 and M2 is greater than for neopentane, then isopentane, and then N-pentane. You can see here. So this is actually highest number. So more the number means more branching. Less is the number of both M1 and M2. Less is the you can see it's kind of linear molecule. So hope you understood calculation of M1 and M2. The next one is actually the Platt number. So the plot number is also another topological index that measures the degree of branching in a molecular graph by counting the number of adjacent edge pairs. So edge pairs. Okay. So the plot number is denoted by Fg. It is defined as the total sum of the edge degrees. Edge degrees. This is with respect to edge. Please remember, plot number is calculated from the edge, but the Zagreb number 1 and 2 are calculated based on the degree of vertex. It is from the vertex. This is from the edge. So keep that in mind so that it will be easy in a molecular graph. What is the significance of this plot number? So it quantifies branching in molecules, distinguishes linear, branched, or cyclic structure. It's useful in both QSAR and QSPR studies, and it correlates with boiling point, stability, reactivity trend. So higher plot number means more branching. So the formula is this one. So this is represented by f of g. F of g is equal to the sum of the vertex 1 to m, means the degree of edge. This is the degree of the edge. So each edge you should consider as a one unit, and the number of neighboring edges should be the degrees of that particular edge. So G is the molecular graph, M is the number of edges, the bonds. This is actually the bond, number of bonds. Total, if 6 bonds, so then there will be M is equal to 6. D means the degree of edges, ith edge. Okay. So this is the simple formula. So let us follow this. However, there are some reports, they've also given this formula f of g is equal to 2 into this dv by 2, like something like this. But this is with respect to the vertex. Okay. This is calculated from the vertex. But however, you just ignore this. This will be complicated to understand. It's just better you calculate from the edge. The edge is better. So this we can also calculate from the vertex, but let us not confuse with the vertex here. So overall, this f of the plot number g, it's also is equal to 2 into p. P is actually the normalized plot number. So generally, this is the advanced one. Plot number is represented by p in the recent days. Earlier, in most of the textbooks, the plot number is used to represent only with f of g. But now we are representing by using p. So p is just half of f of g, normalized plot number. Okay. Let us understand the calculation of the steps involved in the calculation of plot number f of g. For that, it is actually edge based. I'm explaining only the edge based so that it will be easy. If you consider vertex means, it will be a little bit confusion. So just considering edge based, let us understand how to calculate plot number. First step is you should write the molecular graph and identify all the edges, the bonds, label them as A, B, C, D, or whatever. For each edge, count adjacent edges. That is called degree of edge. So degree of edge. So just add that all the degree of edges, you will get the plot number G, f of G. So that plot number, each edge is equal to CC bond. Adjacent edges is equal to bond sharing the common carbon. So the edge degree is degree, number of adjacent. So the P is equal to half of that f of G, normalized. Let us calculate the plot number for this the same isomers that we have discussed in detail about for calculating the Zagreb 1 and Zagreb 2 indices. Pentane, isopentane, and neopentane. Here we should not label the vertex. Here we should label the edges. Okay, that is very, very important. Let us calculate for the plot number for the linear chain pentane. So we know that the pentane, the molecular graph is represented like this: C1, C2, C3, C4, 5, C5. Here C1 and C2 is one edge. We can call this as A or B or C or D. So there are actually 4 edges: A, B, C, D. So the edge A is actually, this is C1, C2, C2, C3 is B, and C4, C5, C3, C4 is C, C4, C5 is D. So these are the edges. If you look at that A edge, this edge, is connected to another edge. That is, what is the another edge? B. So therefore its degree is 1. So its degree is 1. However, if you take the edge C2, C3, that is B, it is connected to this and this. It is connected to this edge and this edge, right? So therefore adjacent edges are 2. Therefore the degree is 2. Similarly, for the C, the edge C, that is C3, C4, it is having 2 edges, 2 neighboring edges, that is C4, C5, and this is for this, the adjacent edges for A is B, and for B is A comma C, and for the edge C, that is C3, C4, the adjacent edges are C3 is B and D, and for D, it is adjacent is only C. So therefore the degree is 1, 2, 2, and 1. So f of g is the sum of all this. That's it. 1 plus 2 plus 2 plus 1, it will be 6. So this is the plot number 6, that is for pentane, f of g. The normalized plot number is half of this. So p is actually 6 by 2, it will be 3. This is the normalized. Similarly for isopentane. So isopentane, let me explain isopentane. Let me explain the calculation of plot number. So isopentane is this one, right? So this is isopentane. You just label this as A, B, C, and D. So there are 4 edges. Okay. So here A is the adjacent edge is only B. So therefore, sorry, this what happened to this. Just calculating. So this is edge A, B, C, and D. There are 4 edges, right? So the A edge, the adjacent is just 1. So therefore its degree is 1. Then if you take B, B is actually B is attached to A, B is attached to D, B is attached to C. So therefore its degree is 3. Then if you take C, C is attached to D and C is attached to B edge. So therefore its degree is 2. Then another edge D. D is actually attached to the next adjacent edge. Edge is C and also the B. Okay, sorry, this B is attached to A, D and C. Correct. This is correct, and this is correct. So for D, it is attached to C and B. So therefore, its degree is 2. So the plot number f of g for this is the sum of the degree of edges. So degree of edges. This is the sum of degree of edges, right? So degree of edges is 1 plus 3 plus 2 plus 2. So this will be 8. So 8 is the plot number. Normalized plot number is f of g divided by 2. It will be 8 by 2. So 4. Okay. So this is how we calculate the plot number for this. Similarly, calculate. Let me calculate for. So see, this is 8. Okay. So let me calculate the plot number for neopentane. Let us understand how do we get this 12 for this. How do we get this 12 for this? Let me calculate for neopentane. So how many edges? Let me define this as A, B, C, D. So there are 4 edges, right? So first find out for each edge. Edge A, how many neighboring edges? A is attached to B, C, and D. So 3 edges. So A is attached to this edge, A is attached to this edge, A is attached to this edge. So therefore its degree is 3. And similarly B, this edge. So B is attached to C, B is attached to D, B is attached to A. So C, D, and A. So its degree is 3. Similarly for C, the edge C with respect to C is attached to B, A and D. So therefore this the degree of this also 3, A, B, C, D. And the last edge D is again the neighboring edges. D is connected to C edge and B edge and A edge. So therefore this is also 3. Okay. So therefore f of G is equal to degree of the sum of degree of edges. So these are all degree of edges. So it will be total this will be 3 plus 3 plus 3 plus 3. This will be 12. So plot normalized plot number f of P is equal to f of G divided by 2. So 12 by 2. It is equal to 6. So this is the plot numbers for the neopentane. Okay. So I have just given how to calculate for this. First you should identify the skeleton, then identify the edge and the degree of edge. First you should identify and you should calculate 6, 3 and 8, 4 and 12, 6. So this is the normalized plot number and this is the plot number. Okay. So this is how this is with respect to edge. Plot number is with respect to edge. Zagreb 1 and Zagreb 2 is with respect to vertex. Okay, next let us take some more examples to understand the plot number for cycloalkanes. You can see that the cyclopropane, if you take this as A, B, C, so A is having the degree is 2, 2 and 2. This is also 2, 2, 2. 2. These are all 2, 2. The degree is 2 because they have shared the 2 edges, right? If you take this edge, if you take this as this one, B, C, D, E, F. For A, this B and F are the adjacent edges. If you take the cyclopropane, C1, C2, it is C2, C3, and there are 2 degrees, 2, 2, 2. Similarly, for cyclobutane, each edge is having neighboring 2 edges, therefore the degree is 2. So this is also for all molecules 2, 2, 2. The degree is 2, 2. If you just add all of them, we get the plot number f of G. So 3 2s are 6, 8, 10, 12. So this has 3 degrees, 3 edges, 3 into 2, 3 edges, and the each degree is 2. So therefore 3 2s are 6 f of G. The P is half of that, 6 by 2. So it will be 3. So the interpretation is each bond is adjacent to 2 others. So this is the smallest ring. Plot number is smallest ring. So smaller the ring, lowest ring size, minimal bond interactions. Cyclobutane, if you take, there are 4 edges, and the degree of each edge is 2. So therefore 4 2s are 8. So that is f of G. Half of that is P, that is 4. So it uniform adjacency in 4-membered ring. So it's moderate bond interaction, simple cyclic topology. Similar cyclopentane, there are 5 edges, and each the degree of each edge is 2. So it will be 10. F of G, half of that is P, 5. So it is a larger ring increases, it means that larger ring increases total adjacent bond pairs, increasing compactness with ring size. Similarly, cyclohexane, so the plot number is 12. So it is the interpretation is the most adjacent bond pairs among listed cycloalkanes. Okay, so more the number, this is the inference. So highest bond interaction can count here. So this is about the plot number calculation. The next one is the third one, the Wiener number. So Wiener number is actually with respect to the distance matrix. One is the vertex. What is Zagreb 1 and Zagreb 2 is based on the vertex. Plot number is based on the edge, and the Wiener number is based on the distance matrix. Okay. So it is a topological index defined as the sum of the shortest path distances between all pairs of vertices in a molecular graph. So this is the definition. The formula for the calculation of distance matrix is this one. So this is of into sigma. This is actually the vertex 1, vertex I vertex, and the j vertex, and this is the distance between I and j vertices. So dij is the shortest distance between the vertices I and j. So this Wiener number represents the molecular size, shape, and it's widely used for boiling point prediction and the stability trends. So let us understand the step-by-step calculation of Wiener index. Let me take the simple example, propane. So first I should write the molecular graph, carbon skeleton C1, C2, C3, and they should only consider only carbon atoms, right? And label the vertices as 1, 2, 3. So this is vertices 1, 2, 3. Construct the distance matrix. For Wiener number, you should always construct the distance matrix. So this is the distance matrix, vertex 1, V1, V2, and V3. And this is vertex 1, vertex 2, and vertex 3. The vertex 1 and 1, the distance is 0. Vertex 1 and 2, it is actually 1. And vertex 1 and 3, they are separated by 2 bonds, therefore it is 2. 0, 1, 2, 1, 0, 1, and 2, 1, 0. So this is the distance matrix corresponding to the cyclopropane. Then add all of them. This is 2, and this is 2, and this is, 2 plus 1, 3, 1 plus 1, 2, 2 plus 1, 3. So this will be 8. So this is the Wiener number. Sum of all the diagonal distances, 1, okay, this will be 8. So this is how we should calculate the Wiener number for the given molecule. So then you get the sum of all of them is 8. And you should apply the formula. It is off into that sum of all the shortest distances between the vertices I and j. So it will be 4. The final answer, the Wiener number for propane is 4. Similarly for pentane, to calculate Wiener number, you should draw the carbon skeleton and then label them as vertices. Then find out the distance matrix. Distance matrix is so this is C1, C2, C3, C4, and C5. C1, C2, C3, C5. These are the vertices, right? So C1 to C2, they're separated by 1 next to that. And C1 and C2, they're separated by 2 bonds. So 1 plus 0 plus, then you should add all of them. Okay. So row 1, first, this is the row 1. You should add 1 plus 2 plus 3, it will be 10. And then row 2, 1 plus 1, it will be 7. Then row 3, it will be 6. Row 4, it will be 7. The sum of all the diagonal elements. And the row 5, it will be 10. So this is the sum of all the dij. So this is dij. Okay. So the total, the sum of all this is about around 40. Okay. The final sum of that will be 40, and you should take the half of that, divide by 2. So 40 by 2 is actually 20. This is the Wiener number for the pentane. So Wiener number increases with the molecular length. Linear alkanes have larger Wiener numbers than branched isomers. So used in predicting boiling point and molecular size. That is the significance of this Wiener number. Okay. So this is the slide showing the comparison of all the 3 topological indices, starting from Zagreb 1, Zagreb 2 indices, Plot number, and Wiener for all the 3 isomers, pentane, isopentane, and neopentane. So this is wrong. This is around 14. So this is spelling mistake. This is a printing mistake. This is Zagreb 1, Zagreb 2. So these 2 are based on the vertex. Please remember, these are calculated based on the vertex. I have already explained. And the plot number, this is second. This is based on the edge, and this is based on the distance between the vertices. This is the degree of the vertices and degree of the edge. So the Zagreb number 1 and 2 are based on the degree of vertices, and the plot number is based on the degree of the edges, and the Wiener number is distance between this is based on the distance matrix. So based on so overall the branching decreases the Wiener number but increases Zagreb number and Platt indices. So that is the inference you can clearly gather. For linear Ito chains, the Wiener number will be high. However, Platt number and Zagreb number will be less. So that is a conclusion you can draw. So these are the only three Zagreb number, Wiener number, and Platt number are the three topological indices that we have actually included in the syllabus. This is very, very, very small, right? Because if you compare the in computational chemistry, if you want to become expert, you have to learn a lot. So you can see that this is one of the slide from the research article that I have just taken. You can see the number of descriptors and types of descriptors that are that should be studied. Its constitutional descriptor is about 48, topological descriptor 119. In 119, I have discussed only 3. Okay, so like that, there are many descriptors to represent the molecular graph in some numbers. So you can see that this is the Zagreb 1, second Zagreb. Okay, and there are various other topological indices, and these are the formulas. So this is only just for the information for you guys. So whatever the thing that you are studying in this is very, very, very minimal. Okay, so with this, I'll just stop my discussion. In my next video, that is the last part of this unit, the fourth recording of this unit, I'll be discussing the QSPR and QSAR. So that would be the last part of this entire unit. Thank you.